In this video, we're going to just take a qualitative look at what some of the different types of steady state error look like, and also briefly discuss some of the common sources of steady state error. So we're going to start by looking at a plot, and on this plot we're going to show different possible outputs for one input, particularly our ramp input. And so these different outputs that we're going to draw on this plot, we can think of them as coming from different systems. So let's say we put this ramp input, which remember from our previous video is just r of t equals t. Again, I could have some scaling factor, but for simplicity right now, let's just say it's equal to t. So let's say I have some system, system 1, which has a response c of t, some output that looks like this over time. So maybe it deviates a little at the start, but as time goes on, it eventually comes back and it lines up well with that output. So again, let's call this output 1. And so what we can say about output 1, which again would be related to system 1, is we can say that our output 1 or our system 1 has 0 steady state error. So 0 steady state error. And the reason we can say that is we go back to our basic definition of steady state error, which is the difference between our input and output as t goes to infinity. And so because these two are the same value as t goes to infinity, we have 0 steady state output, or sorry, 0 steady state error. Let's take a look at a second system. So let's say we have another system which again sort of deviates at the start, and it starts coming back to our second system, but it never really quite gets to the same point, but instead it just sort of goes on in parallel. And so what I've tried to draw here is the red line parallel towards our black line at the end, such that we have some finite error. And so let's see. So actually, let me sort of erase part of this. Okay, so let's take off that bit there. And so what I'm looking at is I want to be at the same point in time so that I can then come in here and say that the difference is going to be our finite steady state error. And so we could say this is E2 of infinity because that's our second input. So let's go ahead and label that as well. So coming over there to our red line, that is our output 2. And so coming down here, let's go ahead and add our notation here that our output 2 is going to have some finite steady state error. And so the reason we can say that it has finite steady state error is because as time is going towards infinity, this output 2 has the same slope as our input. So as t goes to infinity, of course. And so because of that, we have that constant difference between the two. All right, so now let's say we have a third curve or a third system. And so in this case, we have that same deviation and the slope sort of starts coming back, but it never actually gets to where it's even parallel, but now we have a different slope. And so let's call this our output 3. And so in this case, you can kind of imagine if they have different slopes, what's going to end up happening is that they're going to continue diverging. So they're going to continue moving away from one another, our black and our green curve, such that ultimately we're going to have an infinite steady state error as t goes to infinity. So let's come down here and say output 3 is going to have an infinite steady state error. And that's because we have a different slope from our input as our time is going towards infinity. And now, of course, this is only for a ramp input. There are similar things for, of course, a step input or a parabolic input, but I think this is the easiest one where we can see our three qualitative sort of types of steady state error, our 0, our finite, and our infinite. There is a more complete figure in your book which has at least 2 of those outputs shown for a step input as well. So now let's real briefly talk about where do these sources of error come from. So sources of our steady state error. So one of the 2 things we're going to look at is, or we're going to mention, is beyond our scope, and we're not really going to address it much, and that is nonlinear sources of error. So these include things such as saturation and amplifiers, motor dead zone, so having a little bit of time or a little bit of energy that you have to put in before it starts up, backlash in gears. So these are just a few of the examples which I actually mentioned at an earlier point in the textbook. So if you look on section 2.10 on page 78 in the 8th edition of the textbook, there's a few examples like I mentioned there, but it's only a couple pages. In general, this is going to be beyond our scope. However, it is important that you should, sort of be aware of that, at least, that nonlinear sources can become a source of steady state error in actual systems. What we're going to focus on in this course, though, is the configuration of the system and the type of input. So configuration of the system and the type of input. And so that's where we're going to spend pretty much the rest of our unit looking at, is sort of how do we deal with different configurations. Ultimately, what we're going to want to do is bring it down to an equivalent transfer function, or in some cases we're going to simplify so we have unity feedback with a forward gain path, and we'll focus on that forward gain. And we're also going to be concerned with our type of input. So whether we have a step input or a ramp input, we're going to expect different types of steady state error. And so again, all of these things we're going to come back to later and look at in more detail. But in the back of your mind, be keeping in mind that for any of this to be relevant, we have to know that the system is stable. So if we don't have system stability, we can't really talk about steady state error.